Okay, very good. Looks like you have these problems, so we'll start by taking a look at this. Let me take a look.
Okay.
Okay, now the question here was a little bit vague. I said to predict the reactivity for the molecule. I guess what I meant, though, is we wanted to be more specific and predict which particular atoms would react as well. So in the first example, who would be the basic atom?
The oxygen on top.
And what makes that reasonable?
Because of that negative charge.
Okay, good. That's right. That negative, that's a hidden negative that makes us think that's going to be basic. What other role could it play besides base?
None other that I can think of.
What other role do things tend to play with negative charges?
Nucleophiles.
All right. Is there any particular reason why you rejected that here?
There's no hydrogen for it to lose if it were to act as a nucleophile.
Point to the atom that you're talking about.
The oxygen up here at the top.
Okay. Why would it need to lose a hydrogen?
That's a pattern that we noticed, that nucleophiles, when they attack, they typically lose a hydrogen following so they can lose their positive charge. Oh, I see. I'm sorry. I was thinking neutral. So that could actually be a base or nucleophile so long as it has that negative charge. It wouldn't work in, say, this type of a scenario with the carbonyl with the neutral oxygen, but yeah, that actually could work as a nucleophile because it has a negative charge.
Okay. Yes. So that's something. So that's something that I think has been confusing us in the past as well. I think that came up in the previous session as well. There were a few cases where you said, "Gee, this needs to lose a hydrogen," but remember, it's only neutral nucleophiles that need to lose a hydrogen. It's only neutral nucleophiles that need to lose a hydrogen. Otherwise, if you think about it, what you were saying, if we think about it, doesn't make too much sense. I'll go back to my screen. What role do we expect this to play in a reaction?
The I negative could be a nucleophile.
But notice it doesn't have any hydrogens.
Right.
So
yeah.
we've been giving tons of examples all along of negative nucleophiles that don't need hydrogens. So one good thing here, so that was a mistake, but one good thing here is that when I asked you why they needed the hydrogen, when you remembered why it needed a hydrogen, you realized that didn't apply to a negative nucleophile. So why is it that neutral nucleophiles need to have a hydrogen?
Because they would acquire a positive charge, which they could lose by losing a proton.
That's right. And why do negative nucleophiles not need a hydrogen?
Because once they have donated their electrons or attacked, they would no longer have a charge, and they would not need to lose any protons.
Okay, good. All right. So that's an important thing to have in your notes because I think we were getting confused about that last time as well. Now, if you look at the left-hand picture, in the left-hand picture, what role would you expect the right-hand oxygen to play? So,
You mean this right here?
yeah, I don't know. Let's see, what am I going for here? So would you expect that oxygen, what role could you expect that oxygen to play based on the left-hand picture?
I mean, you could probably say you could say base.
Maybe a base. Could it be a nucleophile?
No,
Because,
because it is a neutral oxygen, which would not be a nucleophile without a hydrogen.
good. Now, considering both resonance structures together, do we actually expect that right-hand oxygen to be basic?
Not really, because there's a hidden positive charge in the
That's
resonance
right.
structure.
So there's two important lessons from the resonance here. One lesson is that the carbonyl oxygen is nucleophilic, which you wouldn't expect from the left-hand picture. One lesson from the resonance is that the carbonyl oxygen is nucleophilic because there's a hidden negative charge. But the other lesson is that the other oxygen is not basic because of that positive charge. So resonance is helpful in two ways. Maybe I should really have asked you to say, predict the reactivity and predict the non-reactivity. That is, I should have said, predict the new reactivity that you wouldn't have expected without the resonance, and also predict the lack of reactivity that you wouldn't have predicted without the resonance. Okay.
Nice. Yeah.
All right. So let's go on to the next example. In any case, you drew the resonance structures correctly. That was an example of a lone pair on an atom that's attached to an atom with a pi bond. Okay?
Okay.
So I'll look at the next example. Okay. So that's an example, again, of a lone pair on an atom that's attached to an atom with a pi bond. You drew the resonance correctly. And here you did specifically mention the atoms. You said carbon 1 and 3 could be nucleophilic or basic. So those are good answers there. Okay, so I'll look at the next. So that's fine. So I'll look at the third example. Again, that's the pattern of a lone pair on an atom that's attached to an atom with a pi bond. You said carbon 1 here could be nucleophilic or basic. So in this case, you got it correct. You included both nucleophile and base for carbon 1. It doesn't need a hydrogen because it has that negative charge.
Okay.
How about the oxygen? The oxygen has a lone pair, so could it be basic?
No, because of the resonance structure, it reveals a hidden positive charge.
So it's probably not very basic. Okay,
Yeah.
good. Okay, so let's scroll down to the next set. Good. So here we have the pattern in the next example of a lone pair on an atom that's attached to a carbocation. You said carbon 2 would be electrophilic. Good. That really could have been predicted without the resonance. That could have been predicted without the resonance, but it's confirmed by both resonance structures that carbon 2 could be electrophilic.
Yeah, I suppose what you wouldn't have seen without the resonance structure is that nitrogen would not likely be nucleophilic or basic.
Okay, yeah. Why do you say that?
Because of the hidden positive charge.
That's right. Yeah, that's okay. Well, I'll be critical of that, even though in a way that's right. Even if all you saw was the left-hand picture, you still wouldn't expect the nucleophile to act. Even if we didn't know about the resonance, we still would not expect the left-hand nitrogen to act like a nucleophile or like a base. Can you see any reason why that is? Even in the left-hand picture, you still wouldn't expect the nitrogen to be a nucleophile or a base.
Yeah, because it's got a carbocation with an incomplete octet. That would be much more reactive.
Yeah, so there's really two reasons. First of all, who do we expect to react in this atom? The atom with the charge. And secondly, just being close to a positive charge already makes you less nucleophilic, even without resonance. Even without resonance, being close to the positive charge would make you less nucleophilic. The positive, even though the positive charge is written on carbon 2, it really spreads out over the molecule. So, for both of those reasons, even without the resonance, we would have expected carbon 2 to be the main reactive atom here, and not the nitrogen. But as you said, the resonance gives us even more reasons not to think of the nitrogen as a nucleophile. Okay, so I'll look at the next example. Here you have the example of again a lone pair on an atom that's attached to a carbocation. And you predict here that carbon 2 could be nucleophilic. And that's a good prediction. That's something that I think we would have predicted even just from the left-hand picture. Even just from the left-hand picture, we don't really need the resonance to predict that in this case. Even in the left-hand picture, why would we expect carbon 2 to react and not the nitrogen? Because carbon 2 has the incomplete octet. So that's the one that's more important to react. Let's go back up. Well, so there's not really much new reactivity here. The most important thing is, what type of carbocation is carbon 2? Primary, secondary, or tertiary?
Primary.
So is that a possible or an impossible carbocation?
It's possible because of resonance.
Yeah, that's the main lesson from the resonance here. The resonance, I'm not saying that you made a mistake because I didn't ask you to talk about that, but the resonance didn't reveal any new reactivity here. It just explained how we could make that carbocation in the first place. Same deal for the earlier example with the nitrogen. In the previous example, what type of carbocation was carbon 2?
Also primary.
So how is that possible?
through resonance.
That's stabilizing the carbocation. Okay. All right, but so I made we noticed a few additional things here, but your answers were correct. So let's look at the next example with the oxygen. Here we have the pattern of a lone pair on an atom that's attached to an atom with a carbon with a positive charge. Same as in the previous case, even without the resonance, we would have predicted carbon 5 to be electrophilic. And that's just confirmed by the new picture. Okay, so let's scroll down. Here we have the pattern of a pi bond on an atom that's connected to the carbocation. So here we predict carbon 1 and 3 to be electrophilic. And here you specifically noticed, I think, normally we couldn't put a positive charge on a primary carbon, but we can here because it's resonance stabilized. So here we do have new reactivity. A naive student would have predicted that only carbon 3 would be electrophilic. But with resonance, we can see carbon 1 is also electrophilic. So that's a good point.
I see.
So what your answer there was good. How do you know which one will be the electrophile? How do you know which one will be the electrophile? Well, that's a topic that you study in the second semester in that case. So let's take a look at the next example. This is pretty similar to the previous example, and you gave a similar answer, so that's good. So I'll look at the bottom example. Okay, that one was kind of tricky because you kind of had to reverse your arrows. First you had an arrow going to the left, and then you had two arrows going to the right. That was tricky, but you did that correctly, so that's good. So I haven't really been focusing on it much, but you know the main thing we were focusing on here is just how to draw resonance structures. But you seem to have picked that up very quickly. I don't know, maybe you already knew how to do that before we started doing this tutoring, but you seem to be doing very well on that. I haven't seen any examples. That's most people have a pretty hard time with that, so that's good that you're getting all those. Just drawing the resonance structures for many people is pretty tough, but you've been getting all those right, so that's good. Okay, so in any case, you said 2 and 4 here would be electrophilic. Yes. So the important thing here is that a naive student would normally not have expected carbon 4 to be electrophilic because it didn't have a positive charge in the first picture. But we saw there was a hidden positive charge in another picture. That turns out to be pretty important in the second semester, this particular type of example. Okay, good.
So on this one, would it have a similar situation where oxygen would not likely be reactive because first you'd want to fill those octets for carbons 2 or 4?
That would be the prediction that you would make from the first two resonance structures, yes.
Okay.
Based on the first two resonance structures, you would not predict the oxygen to react. However, we also have to make a prediction based on the last resonance structure. So based on that last resonance structure, what role could the carbonyl oxygen play?
It could be a weak base.
That's right. And that really is something it could do. So the oxygen here really could be a weak base. That doesn't have to leave an incomplete octet on carbons 2 and 4 because you could start with the third resonance structure.
Okay.
You could start with the third resonance structure and just protonate the oxygen, and that would not leave an incomplete octet on 2 and 4. That really is real reactivity here. Oh, so I didn't notice. Did you write that before? Yeah, I see now you have oxygen base. So yeah, that is a third type of reactivity that we should definitely predict in this case. Okay. The oxygen definitely could be a weak base.
But it wouldn't be a nucleophile because in order for it to be a nucleophile, you'd have to use one of the two resonance structures where it has a negative charge, and on both of those, you would be left with a carbocation.
That's exactly right. Yes,
okay.
Very good. That's very good. I think that's pretty subtle logic. That's pretty subtle, but the way you explain that is exactly correct. So we're starting to get into some somewhat subtle ideas here, but you applied that correctly. Yes. So we would not expect the oxygen to be nucleophilic here, and you know that's the truth. Again, I think I mentioned to you last time, it's kind of amazing that these silly little pictures on paper actually predict the true reactivity. But what we just said is the true reactivity. Carbons 2 and 4 are both electrophilic, and the oxygen is basic, but it's not nucleophilic. So these resonance techniques really do accurately predict the reactivity. Okay, good. So let's move on to the next picture.
Okay.
Okay, good.
Well, I think that could also be nucleophilic. I think I was the oxygen on this.
Let's see.
Um,
This is a
based on
tough one. So this group here is what's called a nitro group. I think we're going to try to talk about this more today. Possibly I shouldn't have assigned this yet because these have special properties. But you should make a note that this is what's called a nitro group. And let's see, what would be the reactivity? We're probably not in a good position to predict that yet. What were your guesses here? You said the oxygen could be basic or nucleophilic. One thing you should have noticed then is you would predict either oxygen could be nucleophilic or basic.
yeah.
Because they both have resonance structures with negative charges. So theoretically that seems right, although I don't think that happens in real life, but that does seem to match our theory. And you asked whether carbon-2 could be electrophilic because it's attached to an atom with a positive charge. Yeah. So I suppose, and then what role would the nitrogen play?
Leaving group.
That's right. Okay, so based on our theory, we would expect the oxygens to be nucleophilic or basic, and carbon-2 to be electrophilic. But I can't actually think of any reactions in OChem where that's what happens with the nitro group. So maybe we'll talk more about the nitro group later. So maybe I shouldn't have quite given you this one yet. So this is a case where maybe I was just boasting about how great the resonance is for predicting the reactivity. And now I have to admit that the resonance here doesn't really predict the reactivity all that well. All right, but anyway, based on our theory, it usually works. But based on this theory, based on our theory, your answers were good ones. Based on our theory, we might expect carbon-2 to be electrophilic or the oxygen to be base or nucleophile. But we'll see maybe later. Nitro groups are kind of a special case, and maybe we'll talk about them more later. Okay.
Okay.
So anyway, you gave a good answer based on the principles we've talked about so far.
Okay.
Do you really need that second arrow? Could you just have an arrow going from the negative oxygen to make a pi bond with the positive nitrogen? Why do you need that second arrow?
That nitrogen cannot receive any more electrons. It's already attached to 4 atoms. I'm trying to think of the right wording for the principle.
You described it pretty well. That was a good description. Okay. So the nitrogen already has a complete octet. It can't gain a bond without losing a bond.
Okay.
That was pretty close to what you were saying. So the key thing is that might be surprising to people. So does the positive charge on this nitrogen mean it has an incomplete octet?
No. Only carbon with positive charge.
That's right. That's the one thing I wanted to emphasize here. So you saw that correctly. So this was the pattern of a lone pair on an atom that's connected to an atom with a pi bond. You basically fulfilled that pattern here. One moment. Okay, so let's look at the next example. The oxygen here could be acidic. That's a good point. It certainly could. A weak acid, usually. Carbon-1 could be electrophilic. Carbon-2 could be nucleophilic or basic. Let's see. Okay. Why did you put a question mark next to carbon-1 electrophilic?
Well, in the situation where carbon-1 would be attached to an atom with a positive charge, the oxygen, that would seem to make it a good electrophile, but it also has it's also attached to a molecule with a negative charge, so I didn't know if that kind of negated the effect of being attached to a positively charged atom.
Okay, excellent. That's great. So you're going through some very good thought processes here. And you're also noticing when you're not quite sure. That's good too. It's important. Oftentimes students just totally freeze up when they're not totally sure. So it's good that you're still trying to think clearly about the cases where you're not sure. So that we're developing some good thought process here for OCHEM. That's the right way to think about it. And so your hypothesis here was correct. It's true that carbon 1 is connected to an oxygen with a positive charge, but it's also connected to an atom with a negative charge. So it's really not electrophilic.
Okay.
So as you said, that comment you made was correct. It's really not electrophilic because it's also attached to something with a negative charge. Carbon 2 really is nucleophilic. Carbon 2 is nucleophilic. Now, it's less nucleophilic than it would be if the positive charge wasn't there in the molecule too, but at least the positive charge isn't right next to it. So anyway, and also it has a full charge right on carbon 2. There's a full charge on carbon 2 here, so it certainly is nucleophilic. Okay, so anyway, the oxygen could be acidic, and very important, carbon 2 here could be nucleophilic, or perhaps basic. Those are good answers. And that was a good, sophisticated way to kind of try to think about this. All right, and you drew the resonance structure very correctly. You had the situation here of a lone pair on an atom that's connected to an atom with a pi bond, so I think you're making good progress on that. Okay, I'll look at the next example. Who here is the basic atom?
On carbon 2 with the negative charge.
Oh, I'm sorry. Let's move on to the next example.
Okay, so the next one. Okay.
Yeah.
There it would be actually either oxygen could be.
So that's something we should notice. The whole point of the resonance here is there's two oxygens here that could be basic. Any other roles that could be played here?
Yeah, based on what we were talking about before, with that negative charge, it could actually be a nucleophile as well.
Yeah, so that's kind of a mistake that we left that out. That's a very important reactivity here. Who could be nucleophilic?
The oxygen, either one of the oxygens.
Right. You might have left that out because you were thinking they couldn't be nucleophilic without hydrogens. But we saw that was a mistaken way to use that idea. They don't need hydrogens if they have a negative charge.
Yeah.
Okay, so let's move on. Okay. So the nitrogen could be acidic, or carbon 2 could be nucleophilic or basic. See, here you said it could be nucleophilic even though, well, it does have some hydrogens here. Okay, so in any case, that's the right answer. And that's the correct way to do this. How can you tell whether an atom has a complete octet? They all do, except carbon with a positive charge. Yeah. Now, it's a slight simplification. There are some other things that are incomplete, like H+ and neutral metals and semimetals, but what we said was those were not very important for resonance. So for purposes of resonance, the only important atom without a complete octet is the carbon with the positive charge. So what you said was on the right track there. There are a couple other things that have room for electrons, like H+ or neutral metals or semimetals, and that can be important for reactions. But for resonance, your answer is a good one. Okay, I'll go back to my screen. So that overall, that was quite good. There were no mistakes on the resonance. That was very good. Our main goal here was to learn how to draw resonance structures, and I think we made some really good progress on that. And also, the problems I asked you about reactivity were much harder, but most of those we were getting correct. There was one big problem that's come up a couple of times, though, which is only neutral nucleophiles need to start with a hydrogen. Negative nucleophiles don't. Okay, so let's continue here. Let's see. So what we've been going over for resonance is learning to recognize patterns where resonance is possible. These first three patterns are the ones that we've learned so far and that you were practicing on the homework problems, and you did excellent on those. You recognized all of those perfectly. So let's move on to our next pattern. So the next pattern is a pi bond between two atoms where one of the atoms wants electrons more than the other. Tell me when you have that down.
Okay, yeah.
Okay. So see if you can come up with any resonance structures for this molecule on your screen.
Okay.
Okay, good. Do you see how this fits the pattern we were talking about? So here we have a pi bond between carbon-2 and the oxygen. Who wants electrons more in that situation?
The oxygen.
That's right. How do you know?
It's further to the right on the periodic table.
That's right. It's further to the right. The term for that means it's more electronegative. But what does electronegative mean? It just means it wants electrons more. So the oxygen wants electrons more because it's more electronegative further to the right in the periodic table. Good. So that's this new pattern for resonance. Notice that we never have to worry about breaking the octet rule with this type of arrow because we're not forming a new bond. The only way that you could possibly break the octet rule, or the only way you could exceed an octet, is by forming a new bond. But this arrow is just forming a new lone pair. So there's always room for a new lone pair. There's always room for a new lone pair, but there's not always room for a new bond. Of course, now we have an incomplete octet on carbon-2, but that is permissible for resonance structures. It's okay to have incomplete octets on carbons. You just can't exceed an octet. Okay, so let's see. So that's very good. Let's see how we could predict reactivity here. What would you predict about the reactivity for the compound on the left? Using the first resonance structure, what reactivity would we have predicted?
Well, the oxygen on the carbonyl could be a weak base, or carbon-2 could be electrophilic.
What would make carbon-2 electrophilic?
The delta positive charge.
That's a good point. The delta positive charge, yes. And the oxygen could be a weak base. That's right. You would not expect that oxygen to be nucleophilic. Why is that?
Because it's a neutral oxygen, it would need a hydrogen for it to be nucleophilic.
Okay, good. So based on the left-hand picture, we would expect the carbon to be electrophilic or the oxygen to be a weak base. Now, what reactivity would we predict based on the right-hand picture?
Carbon-2 as an electrophile would be the most reactive.
Yeah. Based on the right-hand picture, we would focus on carbon-2 because it has an incomplete octet.
Yeah.
So notice those two pictures really complement each other. So overall, what reactivity do we expect? Combining what we learned from the two resonance structures.
Either oxygen as a... Well, I guess overall, it'd be most likely to have carbon-2 as an electrophile. It seems, at least, that way. Yeah, I guess you could have oxygen as a weak base.
Right. Now, we're not quite putting that right. So really, they're both quite likely. The oxygen could be an electrophile, or the carbon could be an electrophile, or the oxygen could be a weak base.
Okay.
You might be saying, because the idea that the oxygen could be a weak base is based on the left-hand resonance structure. But that still is a resonance structure. We don't need to worry that if the oxygen is a weak base, we don't need to worry that that's going to leave an incomplete octet on carbon-2. It doesn't have to leave an incomplete octet on carbon-2. If you just started with the left-hand picture, then you could protonate the oxygen and carbon-2 would not have an incomplete octet.
Okay.
In fact, do you know what's the name of this type of functional group?
Ketone?
That's right, it's a ketone. That's right. Or just more generally, it's a carbonyl. Well, you and I have seen many examples of protonating carbonyls to start off a reaction, right? You and I have seen many examples where when we're under acidic conditions, we very often start by protonating the carbonyl oxygen. So we don't always start with the carbonyl carbon as an electrophile. All right, so I would say overall, this resonance wasn't really all that important or very helpful because it didn't change the reactivity or tell us anything new. So this is real resonance. You might need to know it in case you're just asked to draw resonance structures. But this resonance didn't really teach us anything about the molecule that we didn't already know. In this case, the resonance didn't really teach us anything that we didn't already know without the resonance. I think that's oftentimes the case for this type of pattern. This type of pattern is maybe a less useful pattern to draw just because it doesn't usually teach you anything new about the molecule. But in any case, you drew that correctly. I'll go back to my screen.
Okay.
So to review, how can you tell which of two elements is more electronegative?
Depending on how far to the right it lies on the periodic table. The further to the right is more electronegative.
And what does electronegative mean?
Means that it wants electrons.
That's right. Now, what about if you're comparing two elements in the same column? Then they both are the same distance to the right. If you're comparing elements in the same column, how do you figure out who's more electronegative?
Then you go up. Whoever is higher, then that is more electronegative. Whoever is closer to fluorine.
That's a good point. These are some important rules to have in your notes. This turns out to be very important because chemistry is all about transferring and sharing electrons. So these are really crucial ideas to know who wants to take the electrons and who wants to give the electrons. So when I say the higher element, I mean higher in the periodic table. And to the right, we mean to the right in the periodic table, as you were seeing.
Okay.
So theoretically, you might think that there might be a contradiction. You know, what if one element is further to the right, but also lower down in the periodic table? Then these two things might seem to contradict each other. But for organic chemistry, it's usually which is further to the right that matters the most. So for organic chemistry, we usually just focus on which element is further to the right. We usually only have to focus in OChem on how high you are if they're both in the same column. So these rules don't work for all elements. These rules don't work for all elements, but they work for the examples you're usually going to see in OChem. For the examples that matter in OChem, these rules are pretty much what we need. Okay, so we call these the OChem rules for electronegativity. All right, good.
So like chlorine and oxygen, because they're both, pretty far right, yet chlorine is further to the right, would that be more electronegative?
Well, that would be what you would say following these rules. Now, in reality, I don't think that really works. I think oxygen is slightly more electronegative than chlorine, actually. I'm not sure. I think oxygen is slightly more electronegative than chlorine. However, it doesn't matter because you've never seen a chlorine bound to an oxygen, at least in an OChem problem.
Okay, yeah.
If they're not bound to each other, we usually don't care too much who's more electronegative. So that's what I meant when I said these rules don't always work. They just usually work for the examples you're likely to see in OChem. In OChem, you usually don't have to compare chlorine and oxygen electronegativity. So okay. These rules actually probably don't work precisely if you're comparing chlorine and oxygen, but we won't worry about that because in organic chemistry, you usually don't have to compare these two elements' electronegativity. So for the comparisons that you're likely to need for OChem, these rules will generally work, is the point.
Okay.
But there are certainly cases where they don't work. They just don't usually come up in OChem too much. All right. Let's try drawing a new resonance structure for this molecule on your screen.
Okay.
Okay, very good. So what will we predict about reactivity here?
I'd say that carbon-2 could definitely be electrophilic, and the nitrogen it would be a possible not electro, but a base, a weak base.
Okay, good. Yes. Now, could you have gotten those predictions just from the left-hand resonance structure?
Yeah.
Yeah. Carbon-2 is already looking electrophilic there. Why does carbon-2 look electrophilic in the left-hand picture?
Because of its delta positive charge.
That's right, because nitrogen is further to the right than carbon. So
Yeah.
this, like I said, when you use this pattern for resonance, this pattern for resonance is actually, in a sense, not so important because it doesn't usually reveal new reactivity. It just confirms the earlier reactivity. So
Okay.
the resonance here didn't really teach us much, but you need to know it just in case you need to draw the resonance. We just gave us the same reactivity as before in this case. Why did you draw the pi bond moving towards the nitrogen instead of the pi bond moving towards carbon-2?
Because nitrogen being further on the right on the periodic table is more electronegative.
That's right.
Once more.
So going back to my screen, I don't know if you remember, previously I made a distinction between totally illegal resonance and just completely insignificant resonance. So this would not be illegal, technically. This is possible. Gives us a possible resonance structure, but it's completely pointless to draw it because it's so insignificant. Remember that the true structure is a weighted average of the different resonance structures. Well, this would give us a resonance structure that gets almost no weight, like, I don't know, like 1% weight in the resonance structure, so there's no point drawing it. So anyway, the point is you did this correctly. The only resonance arrow that's worth drawing is the one that moves the electrons to the atom that wants the electrons more. So the way you drew this was correct. Okay? Okay, so let's try to draw resonance structures here. Okay, tell me when you're done.
Seems like you could also do an insignificant resonance. Trying to remember the best way to do it without having to redraw the molecule. I'll just... Okay, yeah, I'm not quite thinking how to draw that extra resonance without redrawing the starting material. But yeah, there are 3 resonance structures here.
Okay. All right. Now, I guess I would say that was a mistake. You did say this was insignificant, but it's so insignificant that we shouldn't bother drawing it. I might have confused you with the comment I just made a second ago. So my point was that we should not draw the resonance structure where the electrons move towards the less electronegative element. There's no point drawing that. That's just going to lead to confusion. I think I might have confused you with my last comment. So this resonance structure is legal, but it's so insignificant that it's not worth drawing, was the point I was trying to make.
Yeah, you made that clear. I just
okay.
had it.
All right, maybe you were going for something different. Okay. Now, so now maybe so we probably shouldn't say this is insignificant in the same sense. It's maybe not useful, or I don't know. I'm running out of good terminology. Or it's kind of it doesn't tell us anything new. It doesn't tell us anything new.
Sure.
It's not as helpful. Maybe not as helpful. Not particularly helpful because it doesn't tell us anything new, but it might be worth drawing. Okay, good. All right, so you're right. Now that does give us 3 possible resonance structures, although this third one doesn't tell us anything new about the reactivity. But it does help us to, does give us a new resonance structure. Okay, fair enough. So what would we predict about reactivity here?
You could say...
Oh, and you just figured out how to do it. Okay. So it looks like you just figured out how to do it without kind of retracing your steps. That's right. So the point was here that there was... okay, so that's a good, elegant way to draw those. Correct.
Okay.
So what would we predict? That's good. What would we predict about the reactivity here?
Well, you could have the oxygen on the carbonyl from the starting material. It could be a weak base, or it could be a nucleophile, like on this atom here. Carbon-2, because of its delta positive charge, or even carbocation, could be an electrophile. And I think that's about it. So, well, I guess in this case, this other oxygen could be a weak base because of its lone pair of electrons. So, but it's not likely because of a hidden positive charge on there. So
would that oxygen be expected to be a weak base?
No, it would not.
So your second thoughts there were your better thoughts. Your second thoughts were your better thoughts. This is a little bit, we're getting pretty subtle ideas here, but if there's any resonance structure where something has a positive charge, it probably won't act like a base or like a nucleophile. And if there's any resonance structure where something has a negative charge, it probably won't act like an electrophile or like a leaving group. This is kind of subtle. So sometimes one resonance structure can kind of cancel out another resonance structure, and sometimes it can't. But if there's any resonance structure where you have the wrong charge for a role, you're not going to play that role. So if there's any resonance structure where something has the wrong charge for a role, a charge that would go against the role, it won't play that role. Okay. I haven't quite spelled that out carefully before. But anyway, your second thoughts there were your better thoughts. We would not expect this oxygen to be basic because of that resonance structure where it has a positive charge. Okay. Okay, so overall, I think we got the reactivity there, and you came up with some good resonance structures. I'll go back to my screen.
Okay.
Kind of a simpler way to do this, if you wanted to draw all 3 resonance structures, would have been just to start with this. And then draw this. This would be kind of a simpler way. You were kind of struggling here to get all 3 of the possible resonance structures, so here's the simpler way, without having to kind of reverse your arrows to get all 3 of them.
Yeah, I see.
Now, in many cases, okay, good. Since this resonance structure doesn't really tell us anything new, it's often skipped. If your goal is to draw all the resonance structures, this is the way to do it, or the way you did it is fine. But if your goal is only to draw the resonance structures that give us new information, whoops, if we only want to draw the resonance structures that give us new information, we could just draw these 2. because this gives us the new information that this oxygen is not basic, which we might have expected from this picture. And this doesn't really give us any new information. All right, so in any case, this is an example of this pattern of a pi bond between two elements where one's more electronegative, and it also tied into another way of drawing resonance as well.
Okay.
So here's that rule we were talking about. I had to put in the word probably here because I can maybe think of one or two exceptions to this. So there's always rules and exceptions in OChem. There might be some exceptions to this, but generally a wrong charge will prevent reactivity of those types. Okay, tell me when you have that down.
Okay.
So let's try to come up with another resonance structure here.
Okay.
Okay. So what reactivity would we predict here?
Carbon 2 as electrophile, or the oxygen as an acid.
Excellent. Good. Good. Those are both good. Now, those are both things, again, we could have predicted just from the first resonance structure. So again, this is a pattern that's not too helpful because it doesn't give us any new reactivity. We could have predicted those both from the first resonance structure. But anyway, those are both correct. Good.
Okay.
Why did you move the electrons towards the oxygen and not towards carbon 2?
Because of the electronegativity being greater on the oxygen.
In this case, I would say that's not really the most important factor.
Oh, okay.
So think again, what's the more important reason to move the electrons towards the oxygen and not towards the carbon?
The positive charge.
Right. What's the most important factor in organic chemistry?
The charges.
So whenever we see a charge, that's what we want to try to use to explain things. So
Okay.
in this case, it's the charge that's more important for explaining what's happening here. Of course, they both, in this case, they would both go in the same direction. But in this case, it's more important to use the charge to explain why we're moving the electrons towards the oxygen and not towards carbon-2. Okay, good. I'll go back to my screen. So this is why, when we wrote down the patterns, this is why I didn't just say a pi bond between two atoms where one of the atoms is more electronegative, because that doesn't quite cover all the cases. In the example we just saw, it wasn't just that one was more electronegative, it was one of the atoms wanted electrons more than the other because of the positive charge. So that's why I didn't specifically talk about electronegativity here. One reason why an atom could want electrons more is electronegativity. But another reason why an atom could want electrons more is a positive formal charge. So I wrote this pattern like this so we could cover both of those cases. Okay. Okay, let's try drawing resonance structures here.
Okay. Okay.
Okay. Can you see any problems with that middle resonance structure?
Well, it seems odd that it's between two negative charges, and it's a primary carbocation.
Let's see. Well, it is true that we are forming a primary carbocation here. Is this a primary carbocation that's possible or impossible?
It seems to be possible with the resonance.
So, okay. So that's not really the issue, because the resonance stabilization makes a primary carbocation here possible. We haven't quite put our finger on it. The problem is just that there's so many charges. Does nature like charges?
Oh, good point. We don't want... Well, seems like we can handle two charges with resonance, but we don't want three or more.
Yeah. In fact, that was one of the specific rules we talked about in an earlier session, I think in our last session. We haven't really practiced it much, though, so it would be easy to have forgotten that. I mentioned that rule, and then I didn't give you any practice with it. But that's the purpose of this example. So the rule is don't form three charges. The rule, if you recall, is resonant. Like you were just saying, don't do resonance structures with three charges. So we wouldn't draw. That's better. Excellent. So you're making the fix here. Good.
Yeah, that would make more sense. It did seem kind of weird.
I noticed that you kind of paused before you started here, so perhaps you were maybe thinking about that. Okay, yes. Now, that middle resonance structure, again, is not totally illegal, but it's so insignificant, it's definitely not worth drawing.
Okay.
That middle resonance structure is not completely illegal. He didn't break the octet rule or anything, but it's so insignificant, it's not worth drawing. So this is a case where, so in this case, we're kind of going to skip that pattern. You do here have a pi bond between two elements where one's more electronegative than the other, but that didn't turn out to play an important role here. You can kind of see the point here. The main thing that we need to do here is, what's the main problem this molecule has?
It's charged. It has negative.
Yeah, so the first resonance structure, the main problem is the negative charge on the oxygen. So it should stand to reason that the molecule is not going to kind of waste time, so to speak, with resonance structures that don't deal with that problem. There's no point creating two new charges when we haven't dealt with the charge that that already exists.
I see.
Is another way of looking at it. The whole point of resonance is to find a way to stabilize that negative charge here. There's no point drawing a new resonance structure that's not going to help to stabilize that. Notice how now we do have a resonance structure that does help to stabilize the negative charge because it moves it to a different atom.
Yeah.
Okay. So that's another way to see why that resonance structure was not significant. Again, the most significant factor in OChem is the charges. The main purpose of resonance is to stabilize charges. If you keep that in mind, that can help you to draw the significant resonance structures. Okay.
Okay.
So, going back to my screen. The purpose of this example was to compare this example with, say, this one. I wanted to compare these two examples. Notice here we had 3 resonance structures. In this case, there was a significant resonance structure where we moved the pi bond up to the oxygen and left a carbocation here. But in this case, we don't bother with that resonance structure. What's the difference? Why is this middle resonance structure significant here, but it wasn't significant in the top case?
The charges. There were no charges to begin with to address initially in the first
That's one good way to put it. Yes, that's one good way to put it. And the other way is just to say, here, this only gave us 2 charges. Whereas if we tried to pull the same move up here, we would get 3 charges. Both of those are good ways to think about it. The simplest thing is you could just say, avoid putting in 3 charges. But what you said was correct as well. Okay. So maybe that's an important thing. You don't follow this pattern if it causes you to end up with 3 charges. We don't follow this pattern if it would cause us to end up with 3 charges.
Okay.
Okay, so let's try drawing resonance structures for this picture.
Okay.
Okay, good. Good. So I'll go back to my screen.
Okay.
What about this? Would just drawing this arrow give us a significant resonance structure?
No, it would create 3 charges.
Okay, right. So, good. Would this give us a significant resonance structure for this molecule?
Yeah, that could work.
Because there's not already a charge.
Yeah.
So it's okay to create 2 charges, but not 3.
Yeah.
So this is not good. This is good. Okay.
Okay.
All right, next we have to talk a little bit about NO2. This is what's called a nitro group. These play an important role in the second semester. We should memorize that the Lewis structure of a nitro group looks like this. We did an example with this a bit earlier. Notice this is kind of a maybe might not be what you expect. If you looked at this, you might not have expected the nitrogen to have a positive charge and the oxygen to have a negative charge. That's why I'm saying you should kind of memorize this. This is a kind of surprising Lewis structure with surprising formal charges. Okay, so this is what a nitro group looks like. Notice that the nitro group already starts with 2 formal charges. So this is an exception to the rule we were just talking about. With a nitro group, it's okay for the molecule to have 3 or 4 charges. Maybe I'll put it this way. Tell me when you have that down.
Okay.
So this here is the rule we were just talking about, and now here's an exception. Normally you don't want to draw 3 charges, but that's okay if the molecule has a nitro group. You could kind of say, well, the nitro group always has to have 2 charges. There's no way to get rid of these 2 charges. There's absolutely no way to get rid of these 2 charges. So in a sense, they kind of don't count. That's not really an explanation, but I guess we'll just have to memorize this. So we'll just have to memorize that with nitro groups, it's okay for molecules to have 3 or 4 charges. Even 4 charges can be okay with a nitro group. Okay, so we have our rule and we have our exception.
Okay.
And now we can write down another pattern for resonance. So here's another pattern for resonance, which you can write down.
Okay.
Okay, so let's try drawing resonance structures for this molecule.
Okay.
Oops. Well, I messed up. Let's go back to my screen. I just told you to memorize what the structure was, but then I didn't follow what I just wrote down. So this is what nitro groups look like. Nitro groups look like this.
Yeah.
Okay, so let's try that.
I kind of went through. I don't know. I don't know if this would technically be possible, but well, no, that wouldn't be resonance. Okay. Yeah, that's what I've got.
Okay, so the resonance structure you've drawn so far is just using that pattern we were just talking about. We have the pi bond connected to the nitro group. This doesn't really quite fit into any of the earlier patterns. This doesn't quite fit our earlier patterns. For one thing, this is not, I just told you that you should try to deal with the charges, and this is not dealing with the charges, it's creating two new charges. But we just learned that this is a pattern that really does work for nitro groups. Notice that you created 4 charges. Is that okay to have 4 charges?
With the nitro group, it's okay.
Yeah, we just memorized that that happens sometimes with nitro groups. Okay. Then you were kind of puzzling or wondering about a different approach or a different approach. You might have been on the right track there. So why don't you draw out what you were thinking about, and we can talk about it some more.
I think the idea I was toying with was more of a reaction arrow where the leaving.
Try drawing it out, and we'll take a look at it.
Okay. Yeah, I think. No, that wouldn't work.
Okay. All right. Yeah. All right. That's fine. Let me go back to my screen.
Seems like if you did something like that, but
like what? Ah. Let's see.
I'm not sure that would quite work. We're not really addressing that carbocation, so that's why I'm not sure that this.
Yeah, that wouldn't be so good because that would just leave the carbocation handy.
Okay.
We wouldn't want to do that. Well, let me think there. I guess this example is kind of confusing. Let me think about that for a moment. That doesn't really break any of the rules, what you were thinking of. So that's a good thought. What you were thinking of was a good thought. We're not going to bother drawing it because it's not actually usually considered as a significant resonance structure here for nitro. I guess nitros are just a little bit weird. They maybe just have to memorize what the common patterns are. Because there's actually there's no particular reason. I can't see anything particularly wrong with what you were trying to do. That was a good thought. It's just not the way it's usually drawn. So I'll go back to my screen. Nitros, I guess, are just kind of a special case that have to be learned a little bit separately. So I'll go back to my screen. Maybe the normal rules don't help us too much for nitro groups. I'll go back to my screen. One other thing you could have drawn here, you could have done this. If you see what I'm saying.
Yeah.
Okay. That, of course, doesn't involve this pi bond, but this is still a perfectly good resonance. And then we could move the resonance like this.
I see. Yeah.
I'm not saying that's super important or anything. There's not any huge importance of this, but if you actually had to draw all the resonance structures, this would be, it's useful to see that the negative charge can be on either oxygen. Okay, all right, so I guess maybe the nitro groups are a little confusing. Maybe we'll come back to those later. So I just wanted to point out nitro groups can be important. They can have more than 3 charges, 3 or 4 charges. These are the types of resonance structures that are usually drawn here for the nitro group. This might not just quite, possibly doesn't quite follow all of our earlier rules. Maybe we'll come back to that later. Okay.
Okay.
That's kind of a special case. Would we generally consider this to be a significant resonance arrow?
No, the carbon on either side is equally electronegative, and they don't, neither of them want the electrons more than the other.
That's right. So this would be, this is legal, but it gives us a very insignificant resonance structure that's not worth drawing. There's no point moving a pi bond between atoms if there's no push, basically. There's nothing here pushing this.
Yeah.
There's no reason for this to happen because neither of these is more electronegative than the other. Would this be significant resonance?
Yeah, I think that would.
It looks very similar to before. We're still moving the pi bond between the 2 carbons, but now there's something pushing them. There's a reason to do this. The push is coming from this lone pair. So this is significant. Yeah. This is just the pattern we saw before of a lone pair on an atom connected to an atom with a pi bond. That's one of the patterns we learned early on. A lone pair on an atom attached to an atom with a pi bond. The motivating force here is that lone pairs are less stable than atoms in bonds. So the lone pair wants to get into a bond, and that's what's pushing the pi bond. So there has to be some kind of reason or push to move the pi bond up into a lone pair.
Okay.
Would this be significant?
It's legal. I don't know that it would really tell us more than we already could tell with that structure, but yeah, it would be okay.
Okay, yeah. So we started to, so it is significant. Significant is a technical term. Significant is a technical term that just means that it plays a role in the weighted average. Significant means it plays a significant role in the weighted average. Now, as you were also saying, it might not be too helpful because it doesn't indicate any new reactivity. It wouldn't indicate any new reactivity, but it is significant in the technical sense that, that it plays an important role in the weighted average. Here, the reason to move the pi bond is to get the electrons on the more electronegative element. Okay, so it might be useful to compare these 3 examples. Okay.
Okay.
All right, well, here's the last pattern for resonance. There was quite a few patterns for resonance, but I think we've done a pretty good job internalizing them. So this is not really as overwhelming as it seems. We've been doing a good job seeing these patterns. In any case, here's our last pattern. Tell me when you have this down.
Okay. So like a benzene ring.
Exactly. Good. That's good that you were making that application. That's by far the most important application. So try drawing another resonance structure for this molecule.
Okay.
Excellent. Great. I would say this is a case where it's probably not necessary to number the atoms because we know that we're not going to misdraw this. Okay, good. So, excellent. Are there any other significant resonance structures?
I don't think so.
No, really not in this case. Okay, good. Okay. Now, this doesn't tell us too much about reactivity, but it does tell us, oh, now I'm going to contradict myself. Go ahead and number the atoms, just so it's easier for us to talk about them. So what type of bond is there between carbon 1 and carbon 2? Is it a single or a double bond?
Initially, it's a double bond.
Let's see. Okay, yeah, it's kind of a weird question. Remember that there, in a sense, there's no initial or final because the real picture is a blend of these two pictures.
Okay.
So,
Sure.
although I can see why you would say that because sometimes I talk that way too. But anyway, what I was going for here is, in reality, it's a blend of a single and a double bond is what I was going for. The bond between carbon 1 and 2 is a blend of a single and a double bond. There's also additional issues here because this is also what's called aromatic, and that also changes its properties. But the point is that the bond is a blend of a single and a double bond. Okay, good. Good. Okay, so are there any additional resonance, significant resonance structures here? And if there are, you can draw them on your screen.
Yeah, I don't think there are any.
No, because the alternating single and double bonds don't go all the way around the ring.
Yeah.
So you can't do this because that would break the octet rule on this atom. And there's no point doing this because there's nothing that's really pushing the electrons onto this carbon. There's no reason. This doesn't fit any of the patterns we've seen before. There's no reason to move electrons from this carbon to this carbon in this case. So this wouldn't fit any of the patterns. So that's not really any other significant resonance structures here. So I just wanted to point out it's important that there really be alternating single and double bonds all the way around the ring. Are there any other significant resonance structures here? And if there are, you should draw them on your screen.
Yeah. Yeah, it looks like you can. If you could. Okay.
Okay, excellent. Good. Any other significant resonance structures?
I don't think so.
Okay. Now, what you did here is you said you treated the two rings as one big ring, and you said there was alternating single and double bonds all the way around the big ring. So that was good. But as maybe now you're noticing, we could also do the same thing to one of the little rings.
I see, yeah.
And you'll see that gives us a different pattern than what we've seen before. Okay, good.
I guess you could then... Oh no, that's... Yeah, I think they're just three.
Good. Now you could also say you have alternating single and double bonds around the left-hand ring, but if you drew those arrows, I think you would just get back to your first picture.
Yeah.
Okay. So we need to know when to. If you get back to the first picture, you can just stop. So there was one more resonance structure than we might have seen here originally, because there's more than one ring. There's the big ring, but there's also the little rings on the left and the right. So at first we were missing one of those. That's I'll go back to my screen. That's a more complicated application of this pattern of pi bonds alternating with single bonds all the way around a ring. Sometimes there could be more than one ring structure that you have to take a look at. Okay. All right, well, now we've covered all of these key patterns. We've covered all of the key patterns here for resonance. There's probably some exceptions to this. There's probably some things that that have resonance that don't fall. There are cases of resonance that don't fall exactly into these patterns. I think once you start to internalize the patterns, you just get a feel for resonance, and you can draw even the exceptions. So these cover most of the cases, and there are some cases that probably don't fall into these, but you might start to get a feel for those as we get a feel for these patterns. I think we've been doing pretty good with drawing these resonance structures. All right, so let me. So now I'll give you a few examples that kind of integrate a bunch of this stuff together. Okay, so now let's try to draw all the significant resonance structures for this picture.
Okay. Okay.
Okay, is that it?
Yeah.
All right, good. What reactivity would we predict here?
Carbon-2 could be a weak base or nucleophile. And the oxygen could be a weak base or a nucleophile.
Okay, very good. Excellent. That was right. Good.
Okay.
Okay, let's try this example.
Okay.
Excellent. This is a little tricky to get all the resonance structures, but you did a good job on that. Okay, that's good. So what reactivity would we predict here?
Looks like carbons 1, 3, and 5 could be electrophilic.
Excellent. How about 2 and 4? Would they be electrophilic?
No, they don't have any hidden positive charges.
That's right. Again, this is something that would not be at all obvious to someone if they didn't understand these rules for resonance. But the rules for resonance help us to pick out the exact atoms here that would be electrophilic. Okay, good. I'll write something else down on my screen then. Okay, so let's try drawing the significant resonance structures here.
Okay.
So what reactivity would we predict here?
Carbon 2 could be basic or nucleophilic. Nitrogen could be acidic.
Very good. Excellent. I'm sorry, what were you going to say?
Oh, no, that's all.
Excellent. That was good. All right, that's not easy. That's a good analysis. That's right. Any other resonance structures?
I guess could do this.
Okay, I'm sorry I asked. All right, yeah, so you're right. So that's true. So this does seem to match the rules that we talked about before, although actually we generally would not draw this. So what we're seeing here is the rules don't cover all the cases. We also have to kind of get a feel for this. But you're right, that does fit the rules that we've talked about. The problem is, I'll go back to my screen.
Okay.
Basically what you've done is you just drew the resonance structure you would get if you drew this. Would you expect this to be a significant arrow?
No.
Or, I don't know. Actually, let me think about this for a second. Yeah, we don't normally expect this to be a significant arrow. And for that reason, this is not going to be a significant resonance structure no matter how you kind of get to it, even though you got to it a different way. But it does seem to fit the rules that we were talking about before. Okay. So you did move the electrons up to the nitrogen, which seems like it would want them more. Okay. So so you seem to be you followed the rules as best you could, but that even so, the rules don't always work. In this example, the two that you started with are really the correct resonance structures. And you can kind of see that last one didn't quite make sense because it was just kind of what you would get if you just moved the pi bond from here to here, and there's no real reason to do that. Okay.
Yeah.
All right. So what we're seeing here is that these rules are very helpful, but you also kind of have to just look at a lot of examples to get a feel for what are the good resonance structures. There's a limit to how far we can get with the rules. We also have to try to get a feel. I think you kind of were getting the feel because you didn't draw that last resonance structure until I kind of pushed you to, anyway. So, all right.
Yeah, it always seems a little odd when you end up with a positive and negative charge right next to each other, except for in a nitro group.
Yeah, that might seem odd, but there are cases where that happens. After all, this is considered significant resonance.
True.
And
yeah.
Here we have the negative next to the positive.
That's
so
true.
I'd say this is a pretty tough topic, actually. This is a tough topic. We're seeing that you start by learning the rules, but then you just have to kind of start to get a feel for things as well by just kind of having, I'll just point out resonance structures that are not considered as significant, even if they seem to follow the rules. But I can see why people have trouble with this topic because the rules don't really cover all the cases. Okay, so even though we put in a lot of rules, I give you 6 whole patterns, and that still doesn't really, and I give you a bunch of supplementary rules, and that still doesn't really cover all the cases. But we shouldn't be too pessimistic because overall, you do seem to have a pretty good feel for drawing these structures. Okay, so
maybe just carbons with a carbon positive next to a carbon negative. I don't know that we've seen that happen in resonance, but yeah.
A negative carbon next to a positive carbon.
Yeah,
that's true. So you're trying to come up with a new rule, and that's good. That's good that you're trying to do that. I think you might be right about that. I can't think of any examples off of the top of my head of a negative carbon next to a positive. So you might be correct that. I'm not sure about that, but you might be correct that that's a correct rule. I'll have to keep my eye open to see whether that really works. Okay, but that's good. It's good that you're trying to come up with rules and generalizations. As long as you're kind of thinking about it that way, you should be able to handle the situations. All right.
Okay.
Okay, so let's try to draw the resonance structures here.
Okay.
So how many resonance structures are there total?
5.
Is that fifth resonance structure really different from the first one?
Well, it depends on how you want to look at it. I guess the rings the double bonds are in a different location, but I think I don't know, it seems that within a benzene ring, even though the ring bonds are in a different location, it really doesn't make much difference.
Okay, yeah, so maybe I kind of, so the answer is that they are different. They are different. Maybe it would help to number the carbons.
Okay.
So just so we can talk about them more clearly. So in the very first resonance structure, is the bond between carbon 1, 2 a single, carbons 1 and 2 a single or a double?
Double.
How about in the last picture?
Just a single.
So they're different. Yeah. So they are considered 2 different resonance structures. So I almost kind of bullied you out of it, but you did a good job here of getting all the resonance structures. Okay. They are all worth drawing. Now, in a sense, you might not learn much new about the reactivity here. by drawing that last one, but it's still considered another resonance structure. So you see, you did a good job here. This wasn't easy. You drew the exact right number of resonance structures. You did draw the exact right number of resonance structures.
Okay.
Okay, good. So what would we predict about reactivity here?
It looks like oxygen, it could be nucleophilic, basic, or acidic. But I think, let me correct that. One of the things we said is when it does have a positive charge, it would not likely play the role of nucleophile or base within the resonance structure. So it looks like it would be acidic, whereas within the ring, carbons 2, 4, and 6 could all be nucleophilic or basic.
That was very good. That was very good. The most important thing you did that was good there is that you had second thoughts and thought through some of your ideas. So when you first started talking, you had a couple rules that didn't make sense, but you corrected them. And that's good, that you took your time and had some second thoughts on that. So you did that correctly. Because there's some resonance structures where the oxygen has a positive charge, we're not going to expect it to be nucleophilic or acidic. I'm sorry, we're not going to expect it to be nucleophilic or basic. We might expect the oxygen to be acidic or the carbons 2, 4, and 6 to be nucleophilic. Good. Now, when you study this in more detail, you'll learn that what really happens here is that 2, 4, and 6 are nucleophilic. That's what will actually happen. But based on what we've talked about so far, what your answer was a good one. So that's good. So you came up with a good answer for that. And without the resonance, we couldn't explain why 2, 4, and 6 are nucleophilic and not, say, 3 or 5. This turns out to be very important in the second semester. Remember that benzene is one of the 2 most important types of functional groups in the second semester. This type of resonance is really crucial to the benzene chapter. So now we're starting to get into some important ideas for second semester benzene reactivity. Okay, so anyway, that was a good job on that problem. I'll go back to my screen.
Okay.
Notice what you did on that problem is that you started by pushing this lone pair into the ring. And then you just drew enough, kept drawing resonance structures until you got 5. You could alternatively have started by moving all the bonds around the ring. And then you could have pushed the lone pair into the ring. Either is fine. I just wanted to point out there's more than one way you could have done this. There's more than one way you could have done this. Probably the way you did it is better, though. So why am I mentioning this? I don't know. So I just wanted to point out there is more than one way you could have gotten all 5 resonance structures. Probably the way you did it is the best way. But you could have also used this pattern of having alternating single and double bonds around the ring. But actually, I think the way you did it is maybe a better approach. Okay.
Okay.
Okay, so let's draw the resonance structures here. Okay. So what that's good. So what reactivity would you predict here?
2 carbon 2 has an electrophile. Possibly runoff. I think that's all I'd really expect.
That's very good. You got to know when to stop. That's good. You got to know when to stop. And you would really predict that from either picture. Either picture would give the same prediction in this case. Carbon 2 is this is very clear cut. Carbon 2 is going to be electrophilic. Okay, good. So that was right, and it's good that you didn't keep going when you knew when to stop. There's really only one type of reactivity we would predict here. So that's very good. All right, I'll go back to my screen. Okay, let's try drawing all the significant resonance structures here.
Okay.
Okay, good. So what reactivity would we expect?
Carbon 3. Carbon 3 could be an electrophile, and carbon 1 could be an electrophile. Nitrogen could be a nucleophile or a weak base. I think that's all.
Okay, that's very good again. That's very good. Now, the one thing that's interesting that you couldn't just predict from the first picture is that carbon 1 is electrophilic. All the other reactivity you could have predicted without the resonance. The value added from the resonance here is that carbon 1 is electrophilic. That's something we wouldn't have predicted without the resonance. But in any case, your answer was a good one. Your answer was a good one. I just wanted to point out the resonance told us carbon 1 was electrophilic. All the other stuff we could have gotten just from the first picture. Okay, very good. So that's a good way of drawing the resonance, and also that's a very good, careful job of predicting the reactivity. That's not easy, but that was a good answer. Okay, let's see.
Thanks.
Okay, let's try drawing resonance structures here.
Okay.
Good, excellent. So what reactivity would we predict here?
Carbons 1 and 3 would be nucleophiles or weak bases, and the nitrogen well, maybe carbon 4 could be electrophilic. Yeah, since it's next to an atom with a positive charge.
Okay, let's see. Yeah, okay. That does seem to match our rules. Yeah, so that's a good application of our rules. I don't think carbon 4 generally would be electrophilic here, but that does match the rules we've talked about so far. Okay, so that's a good application of our rules. Okay, good. All right, so that's good. I'll go back to my screen.
Okay.
All right, let's try drawing resonance structures here.
Okay.
Very good.
And I think,
okay. You were saying?
yeah, nitrogen could be a nucleophile or a base, and carbon 2 could be a nucleophile or a weak base.
Or a base. Those are good answers. Yeah, nucleophile or base, depending on what's going on. Good. Okay, very good. That's correct. I'll write something else down. Okay, let's try this example.
Okay.
Okay, is that it?
Oh, I don't think so, actually. That one is interesting. If you're going off of the charges, that last resonance structure seems possible because the electrons would be going toward the positive charge, but it seems a little almost counterintuitive if you're thinking about electronegativity. The electrons going toward a less electronegative atom, but I think it would still work because of the charge.
What's more important, the charge or the electronegativity?
The charge.
Yeah, the charges are most important. Okay, so that was a good analysis, but we should clarify that, yeah, charges are more important than electronegativity. Charges trump electronegativity. I don't know. Do you know what? You ever played a card game with trumps?
I think I've heard of it,
So
but
a trump is, I don't know. A trump is something that's more important than something else, basically. So
okay.
the charges are more important than the electronegativity if there's a conflict. One thing that should make you a little suspicious is we just haven't seen any examples before of two double bonds right next to each other. We should always be a little uncomfortable when we see something we've never seen before. But this does turn out to be a reasonable resonance structure. So this is still legal and a significant resonance structure. Okay, it does fall into our basic pattern of a lone pair on an atom connected to an atom with a positive charge. This is a normal pattern of a lone pair on an atom connected to an atom with a positive charge. Okay, so there was that extra resonance structure here. What would we predict about reactivity here?
Well, you could predict carbon-3 as being electrophilic. The nitrogen could be a weak base or nucleophile. The oxygen, yeah, I don't think the oxygen would play a role. So carbon-3 could be electrophilic and nitrogen could be a nucleophile or a weak base.
Which resonance structure allows the nitrogen to be a nucleophile?
The structure on the right.
Only that one.
Yeah.
Because it couldn't be a nucleophile in the first picture because it was neutral without a hydrogen. And it couldn't be a nucleophile in the second picture because that would leave an incomplete octet on the carbon. So it's only that's the value added from drawing that third resonance structure. Without the third resonance structure, we wouldn't predict that nitrogen would be nucleophilic. So anyway, your answer was a good one. Okay. All right, I'll go back to my screen. Okay, let's try drawing the resonance structures here.
Okay.
Okay, good. That's right. So that's good that you saw that you had to kind of move the arrows one way and then reverse and move the other way to get all the resonance structures. That's good. What reactivity would we predict here?
It looks like carbons 1, 3, and 5 would all be nucleophilic or basic.
Good. By the way, how do you tell? How do you tell whether they're going to be nucleophilic or basic? Well, remember that we saw that one pattern is that oftentimes you alternate. So if we just finished doing an acid-base reaction, then what role would they play?
Nucleophile.
But if we just finished doing a nucleophile-electrophile reaction, what role would they play?
Weak base.
That's right. At least that's the pattern we saw earlier. So that's one thing you might use to figure out what pattern, what role they were actually going to play. You would look at what the previous step was. All right, good. Good. All right. Okay, let's try this example.
Okay.
Okay, good. It was a little tricky to get all the resonance structures here, but you took your time and you figured it out. That's an important skill in OChem, to know when you have to just take your time and figure something out, and you did that. All right, good. So you did come up with all the resonance structures. That was good. And what would we predict here about reactivity?
Oxygen could be a weak base, and carbons 1, 3, and 5 could all be electrophiles. That's all.
That's right. That's good. That's good. That's exactly right. Now, and so what was the value added from the resonance? We already would have predicted carbon 1 was electrophilic, or the oxygen was a weak base. So the extra insight we got here is that 3 and 5 are electrophilic. If someone hadn't studied resonance, they would have no idea that 3 and 5 were electrophilic. After all, what do we normally predict that what role do we normally predict for carbon-carbon pi bonds?
They would normally play an opposite role, nucleophile or a weak base.
That's right. They would normally be a nucleophile, but here we don't expect that because of their hidden positive charges. Instead, we expect carbons 3 and 5 to be electrophilic. So this shows how resonance can be a powerful tool to predict something new. I don't know what the actual history is, but we might expect that this might have been puzzling to the chemists at first. They might have said, oh, we've learned that alkenes are nucleophilic, and they might have been puzzled why these alkenes were acting like electrophiles. And perhaps they had to come up with this resonance explanation to explain it. So in any case, we can see now how the reactivity can change from what you might expect if you don't consider resonance. Okay, very good. So I'll go back to my screen. Okay, that's good. So I think we've been doing really well on this. Like I said, I think this is actually pretty challenging material. We're really integrating lots and lots of ideas. I think you've been doing a really good job with that. A real good job, definitely almost perfect on drawing the resonance structures. That we definitely really mastered that. But also a really good job of predicting the reactivity, which is really we're really integrating a lot of different ideas in the reactivity, and you've been doing a real good job of applying that. So that's good. And I think that definitely will pay off as we go on and you studying the reactions. Those are really helpful skills in OChem. So as usual, it's important to carefully review. Like I said, I think we're doing real good with some very challenging material. The only thing so right now we're in good shape. The only thing to worry about is because it is so complicated, it would be easy to start forgetting it. So it's important to keep reviewing. So here's our patterns for resonance. At this point, you're doing so well with the resonance, maybe you're just kind of doing it by feel without thinking about the patterns, and that's perfectly okay. It's even better if you're getting a feel. But in any case, for the record, here's the particular patterns that we've looked at. One thing that has given us a little trouble is neutral nucleophiles need a proton so that they can lose the proton, but negative nucleophiles don't need to start with a proton. Okay. That's come up. That's given us a little trouble a couple of times. All right, so you can review what we went through today to make sure you're still comfortable with that. But overall, I think so far we've been doing pretty well with this.